Okay, so what should you have done before today? What was due today's class? Chapter 2. Yeah, the 2 learn smarts. Hopefully you've got your iClickers registered. I tried syncing it up this morning. It looks like there's a couple people maybe that still aren't. It shouldn't be a big deal. It'll still record your responses, and if you register it a little bit later, it'll still sync up. But try to get that, registered as soon as possible. Make sure it's registered correctly. I think what I'll do today, just because I know there's some backlogs, backorders of iClickers, is we'll use them today, but it's not going to count for points. We'll kind of get an idea about how they work. Then I'll upload it to Canvas. So if you were here today and you use your iClicker and you don't see anything pop up on Canvas, that'll kind of be a signal to you that you either forgot to register, it's not registered correctly, or we can figure out why that's happening. So they'll be kind of a trial run for those. Once we kind of get to those iClicker questions, I'll show you. For the rest of the week, kind of Wednesday and Friday, we'll be using them for points. So I'll kind of expect that you've got everything, or if something doesn't upload today after this afternoon, I upload them to Canvas, you reach out to me and we get that figured out for Wednesday. Okay? Any questions for me before we jump into it? Okay, so we left off doing a lot of Excel work on Friday. We're doing frequency distributions, so that looks something like, hopefully this marker works. I don't know, let's say we were doing the number of kids in a household. So we've got 0, 1, 2, 3, so on. I don't know. We've got a small data set. We'll just make up some numbers here. This one will make small. Okay. So it says, we did stuff like this. We created in Excel. We got these nice frequency distributions or histograms. We can also do what we call cumulative frequencies, right? So similar to GPAs, right? If I'm looking at your GPA right now, it's for this semester. But your cumulative GPA, it goes all the way back to your very first semester, right? So this idea of cumulative is like, look at the current response or the current bin, if we're doing this with continuous data, which we will in a second, and add up the frequency from this bin and every other kind of response or every other bin or everything that's below it, right? Cumulative, GPA, go from today all the way back to when you were freshmen. Cumulative frequency, go from this bin or this response all the way back to the lowest one, okay? So that's the idea. We can graph these. The book calls them OGIVs. I've never heard that until I had used this book for this class. Really, they're just cumulative frequency graphs or cumulative frequency polygons. We'll see how we do these in Excel. We can do them with relative frequencies or frequencies. So I'll show you an example on the board here where I'm using frequencies, and then once we go to Excel, I'll show you how we would do this with relative frequencies, and it's the exact same thing. Okay? So here's my frequency distribution. If I wanted to do a cumulative frequency distribution, so down here, this is going to be our cumulative frequency distribution. I'll go to the very first response or the lowest response I can see, which is 0 kids in a household. Well, if I do cumulative frequency, it's the frequency of the current response I'm looking at plus everything below it. Well, for the very first response, the cumulative frequency is pretty easy because there's nothing below it, right? So the cumulative frequency for 0 here is just 30. It's the frequency of the current response and everything below it. Well, there's nothing below the very first one. So we'll go up here, right? One's pretty easy. Well, then we go to the next possible response, or the next highest response. 1 kid in the household. The cumulative frequency is the frequency of that response plus everything below it. So the frequency of 1 is 40, plus everything below it. Well, there's only one response below it, which is 0. That frequency is 30, so we would add these up. Right? So the cumulative frequency, the cumulative frequency for the response of 1 would be 70, right? The number of households with 1 kid plus the number of households with 0 kids. Then we go to 2. The cumulative frequency for 2 would be, well, what's the frequency of seeing 2 kids in a household? 25. I think the numbers are messed up here. This shouldn't be 25. Otherwise, we're going to have an issue. This is 15. So we've got the frequency for this response, 15, plus all those below it. So 15 plus 40 plus 30 gives us 85. So the cumulative frequency for 2 will be 85, right? And we just keep doing this process all the way, for a higher number of kids. Any questions on this? I want to show you one other thing with this that maybe might make a little more sense with something. So once we get to Excel, I'm going to do something, and I think an easier way to think about it is if I show you a visual first. So we're all okay with how I came up with the cumulative frequency for 2 kids in a household, right? So it's the frequency of saying 2 kids plus anything below. Well, notice instead of going 15 plus 40 plus 30, if I take the cumulative frequency of the response right before it, that would have been 70. And if I add to that the frequency of the current response I'm looking at, that would give me the same 85. And that's because if I go to the response right before it and get its cumulative frequency, what that cumulative frequency represents is the frequency of this category plus everything below it. So instead of adding them up every single time by hand, I can always just go, okay, well, what was the cumulative frequency for the response right before the one I'm looking at? And then just add the frequency of the current response you're looking at to that, and you'd have the same value, same answer. You guys see that okay over there? Okay. I'm more worried about you guys in the front row there. So let me know if I need to kind of do one of those numbers. All right. I think I might jump. Oh, so this is what we're going to now just create in Excel. And I'll kind of show you how to put these cumulative frequencies in Excel. Pretty easy. It was the last thing that we really had to do for frequency distributions using that enrollments data set. So, and correct me if I'm wrong, we did scatter. I kind of show you some examples of scatter plots on Friday, right? We kind of looked at that vaccination data and we went through that. So these are a little bit out of order. Different sections, I went through things a little bit differently. So let's go to that enrollments blank file. And I saved it wherever we left off last class. So we had those universities, their enrollments, and we created this frequency distribution. If I can get the Zoom thing to go away here in a second, we'll scroll over. So now I'm going to come up with a cumulative frequency. And unlike what I did in the board, which was cumulative frequency, I'm actually going to do a cumulative relative frequency, okay? I believe this is what the completed file has as well. It doesn't have, I think it still said cumulative frequency, but it's the same idea. So instead of taking these frequencies, right, and kind of using those to come up with a cumulative frequency, we're going to use the relative frequencies and come up with a cumulative relative frequency. But it's the same idea. To come up with a cumulative relative frequency, you take the relative frequency of the response you're looking at plus all those below. Right? Well, now instead of individual responses, we have these bins, but it works the same way. So for the very first or the lowest bin, right, the lowest possible responses, the cumulative relative frequency will just be what? So up there, in the example I did in the board, for that first response, the cumulative frequency was the same as the frequency. So for a cumulative relative frequency, what do you think for that first lowest kind of response, what would the cumulative relative frequency be? Anyone? Yeah.
Just the first frequency.
Yeah, you guys are scaring me a little bit, right? So here, the cumulative frequency is just the same as the frequency for that first one. So if we're doing relative frequency, the cumulative relative frequency of the lowest response will just be the relative frequency, right, for that first one. So instead of using the frequencies, we're using the relative frequency. So it's going to be this 0.76. So the first one's pretty easy. You don't have to think too much. For the second one, what's the cumulative relative frequency going to be? Well, we're going to do some math here. So put an equal sign in Excel. It's just going to be the relative frequency of the current response I'm looking at. Now my response is a bin, right? A range of responses, plus all the responses below that. Well, I've got my bins like ordered in terms of smallest to lowest. So I just go this relative frequency plus the relative frequency of the bin below that. Right? Any questions on that? And how am I getting these cell references in here? I'm just clicking on the cell, the numbers in, right? It's that easy. So for the third bin, it'll be the relative frequency of that bin plus the relative frequency of all the bins below it. Everyone okay with that? Any questions? So I could keep doing this, right? And every time I'm just going to have to add in one more additional thing, right? Because I'm just going to go from this bin all the way to the bottom. But there's another way I can do this a lot quicker. I don't have to type it in every single time. So if instead, here, remember what I was saying on the board, the cumulative relative frequency is always going to be the cumulative frequency of the bin below it plus just the regular frequency of that response. So what I can do is say, well, look, I know that every single time when I want the cumulative frequency of this bin, I'll be taking the cumulative frequency of the bin right below it, right? And adding to that the relative frequency of the bin I'm looking, or the response that I'm looking at. And then for the next one, right? Well, what should this one be? It would be, here's the cumulative frequency of the bin right before it, plus the relative frequency of the bin that I'm looking at. Well, if I copy this down, this is going to update instead of S7 and Q8, it would be S8 and Q9, which is what I want, right? So every single time I want to keep taking the cumulative frequency of the bin before it, plus the frequency or the relative frequency of the bin I'm looking at. So when I copy this down, right, and I need to change this, but it looks at the bin or the cumulative frequency of the bin right before it, plus the relative frequency of the bin we're looking at, right? I only had to enter it in one time. Any questions? Like it's a little bit, that's a little bit tricky, I feel like. Yeah.
So it's only the cumulative relative frequency that's right before it and not all of the ones.
Yeah, because if you think about it, these cumulative frequencies say this reflects the response of 1 plus the response of 0. But once I get to here, this is going to reflect the response of 2 plus the response of 1 plus the response of 0. So it's like this cumulative frequency is always going to be self-contained in the next response. Yep. Any other questions on that? What should the cumulative relative frequency, you can see it up here, what should it always be in the last bit? 1, right? So you think about it, you know, if I went up to, I don't know if this is 20 kids in a household, right? The largest we ever see. Once we get to that largest response, that cumulative relative frequency is going to represent the number of households with 20 kids or 19 or 14, right? It's adding them all up. Well, once I go from the highest all the way down to the lowest and I add them all up, that's just every single possible household, right, in my data set. And a relative frequency, that would mean the total number of observations divided by the total number of observations. So it should always be at 1 then. If I instead did this for the percent, so cumulative percent relative frequency, what should that always be once I get to the last bin? 100, right? This is the idea of when we're moving from relative frequencies to percentages, we're just moving the decimal 2 places, multiplying by 100. So if that relative frequency should be 1, the percent relative frequency should be 100, right? And actually, I think if I copy these over, I should be okay. Because notice, when I copy them over one cell, it instead of using the relative frequencies, we'll start using the percent relative frequencies. But everything else will be right. So I think everything should update to where, let's say I wanted to do percent cumulative relative frequency, right? When I copy these over, sure enough, I kind of get the percent relative frequencies. And once I get to that last bit, it's 100, okay? Any other questions here? Now, I could have also just created this by what? Multiplying these by 100, but it you know, just kind of showing you that it doesn't, you know, I saved myself a lot of work here, right, by the way I had this set up. And obviously, I have a little bit more foresight right now into how to set this up, but I am kind of on the assignments, and as we work through things, I'll be setting things up in a way that kind of lead us to making it a little bit easier. And I'll try to mention those things like I just did where, oh, if we copy this over because these two columns are next to each other, this one will just update the cell references appropriately. Okay. So I could then select my labels, hold Control or Command on a Mac, select my cumulative relative frequencies, go to Insert, here's all my graphs. I'll do a line graph that kind of shows like how quickly, you know, across these bins, my relative frequency approaches 1. Okay. Any questions on that? All right, so I might come back to this if we have a little bit of time at the end of class, and we did these time series plots Friday, I believe. So if we look at the Excel file, maybe I didn't. Oh yeah, this was kind of where I created that US Canada data. So I'll make sure I upload this sheet into the completed version as well after class today. Also, because we're doing a little bit more today, I've got them actually queued up in my office ready to go after classes today. I'm going to splice all the Excel stuff we've done together to make one kind of self-contained video. So that should be up there sometime this afternoon or late evening. All right. Any other questions on anything with that? You want to see the Excel again? We can... Okay. So we had these frequency distributions. And, you know, we were keeping the number of bins pretty low just to make it, honestly, I'm introducing the idea, so I'm not going to make it super complicated. There's too much work initially. But you can imagine if I had a bunch of responses, or like on the income one, if I created a bunch of like $5,000 bins, I said usually want to choose somewhere between 5 and 20, but I could choose a whole bunch of bins so that, you know, maybe I end up with something that looks like this. And then if I think about going through the top part of each one, I can kind of get an idea about like a continuous distribution. Right? It's not truly continuous, there's bins, but if I create enough of them, I could almost think about looking at this as though it's like a continuous distribution. So I don't know, if you take a calculus or something, this is how they try to like get you to understand, continuous function and you can break it down to rectangles, but it doesn't really matter. We'll just start thinking about, if we were to draw a line to the top of these bars, that kind of represents the shape of our distribution. Notice here, the majority of the data, right? Remember, the y-axis here, we could do relative frequencies. It's probably better for right now to think of, if we graph it using the frequencies, each one of these bars just represents how many observations had that response. So the bulk of the observations, the responses were in this range, not near as many that were higher, right? Or up here on the right side, or kind of right end of our distribution. So we start to think about different types of distributions we can see. The first one, which we aren't really going to hammer on this probably until after the first exam. But once we get to the end of the first exam, we'll be talking about this normal distribution a lot. Okay? So all a normal distribution means is the bulk of the data, or the highest frequencies, right? The responses we see the most often are kind of in the middle. And as we move away from that to either side, it's kind of a similar drop off. So notice if we were to try to kind of draw a line that best fits the top of these bars, we get kind of what we would call like bell curves, right? It's symmetric, right? It kind of looks like it can fold on top of itself. Doesn't matter if on the right or the left side, it kind of falls away from this middle point kind of equally as quickly. Yeah. So the bulk of the data is in the middle. Yep, so we see like all of the highest bars. That means that's where the highest frequencies are. Or when we went through the data, this is the response that I saw the most number of times, right? The highest frequency. So usually it's kind of the bulk of our observations are right in the middle of that normal distribution. You got to notice once we get to the tails, right? We've got like almost no responses in some of these guys. Actually, in fact, there are some that have no frequencies. Right? So I think here I was using like, I think it was bicep data or average SAT score data for something. So you can kind of see if we look at these standardized tests, the reason they call them standardized is because once you have a large enough sample, or if you have the population take them, you end up seeing that the scores follow a normal distribution. That's why they call that kind of the standardized test. If we look instead at something like income data, so they did $5,000 bins, and then once they started to get to like 200,000, they started creating these larger bins. So this is 200 to 250, and then 250,000 or over. So they had to create some of these catch-alls, otherwise this graph right would just kind of went off into perpetuity. So if we look at this, the bulk of the data is where? Well, the highest bars, the highest frequencies are actually over here on the left side. It's kind of weird. We call it a right skewed data or right skewed distribution. I think we'll get to why today, the technical reason why. But the easiest way to remember a right skewed distribution just has a really long right tail. Right? If I was to draw this distribution, long right tail, it's right skewed. right? So we've got the bulk of the data on the left-hand side, but then we've got some really like small number of extremely high values on the right side, right? So it kind of draws that tail out. We could also see a left skew distribution, same idea. If it's got a long left tail, we call it left skew. So I used the length of pregnancy here, the gestation. You can kind of see most pregnancies are like within this 3-week range. But we do see like quite a few premature births and births prior to kind of that around that 9 months. But we don't see like babies being born at 11 months, right? So there's really like no right tail to this distribution. It's only kind of this long left tail. And then we might have a bimodal distribution. We actually, we'll kind of get some more discussion about these towards the end of the semester. And that's because usually if we look at them, it's not that this isn't a normal distribution. It's that there's an underlying characteristic that is directly related to the mean. And we'll talk about that here today in a little bit. But that characteristic is causing a huge difference in the mean for some particular two groups, right? Whatever that characteristic is. So if we look here, we look at body mass or weight. Why do you think instead of just this is the distribution for weight, we might actually have two normal distributions within there? You can kind of see that, right? Looks like kind of here's one normal distribution and maybe like there's another. So what characteristics might be driving this bimodal distribution? Thinking about weight.
Gender.
Yeah, right. If we look at males versus females, there's an obvious shift in the distribution. So if we were to draw them on their own, female weight kind of looks normally distributed. Male weight looks pretty normally distributed. When you throw them all together, right? And this one, you can really see it. A lot of times the problem is, if I throw it together, it could look something like this, where like the distributions are like closer. And so it looks normal, but it's actually two normals that are just kind of shifted a little bit. So anytime we see something where we see kind of this up and this dip and then back up, we probably want to investigate the data and think about what characteristic for whatever variable we're interested in could be like, really, is there actually two distributions in here? Okay. So that's always an interesting one. Well, like I said, we'll kind of go back to thinking about these in a second. We need to build up a few more topics. So how are we going to describe population or sample data sets? So this is that descriptive statistics. I said we're going to start to develop all these statistics that we want to calculate that tell us something about the data. It's great to have a nice visual of the distribution, but there's other things that we might be interested in, especially when we want to compare. Okay? So the first is a measure of central tendency. I think I've already mentioned today the mean, right? You've probably heard like, the average, right? Where's the middle point of the data, the central tendency of the data, right? Or like I said, easier way to think about it is central tendency, kind of the middle point of the data. Right? So we have three measures, and this is where we'll start using some notation. You know, in terms of memorizing it, once we have to examine things, I give you a formula sheet. However, I am going to like use the mathematical notation quite often. Although when I'm saying it in words, you'll kind of hear what it's called. So notice for the mean, we're thinking about we have population data, and we calculate the mean. We're going to use kind of the Greek letter mu. So anytime we look at population data and we calculate a statistic, we usually use a Greek letter to notate that. X bar, or kind of X with the bar over it, that's going to be a mean if we calculate it from sample data. And we may very well, in fact, calculate them the exact same way. It's just that using this notation, you're kind of conveying to whoever you're showing it to, well, I had population data when I calculated this mean, but this means only sample data, right? So if my sample isn't very big, you might want to be a little more concerned with that, right? It could vary from the population. And I didn't put it up because honestly, it never makes a difference for what we're doing. Technically, for the median and the mode, I wrote this as capital M subscript D, capital M subscript O, the median and mode. Technically, those are population medians and modes. If you wanted the sample mean and mode, we actually just lowercase d out. All right, so that one, it's not in none of the homework or questions will that ever be a thing where I ask you about the difference in notation for those two statistics. But it does play a role more in what we're going to do when we think about calculating the mean. And that's why I kind of highlighted the difference between how we show the population mean versus the sample mean. We also have measures of variation. I don't think we'll probably talk about these today, but definitely next class. And so these will be our variance and our standard deviation. We're going to write the variance for the population as sigma squared. Once again, we're using kind of Greek alphabet here for the population. And then for the sample, we calculate the variance for sample data set S squared. Right? We go back to kind of using our traditional kind of English alphabet. And then the standard deviation is just a scaled version of the variance. So notice the variance here is sigma squared and S squared for the population and the sample. For standard deviation, it's just sigma and S. So basically the standard deviation is just the square root of the variance. And I'll be hammering this home, this idea home the entire week. You'll probably be sick of it by the end of the class. Okay? But we're just scaling the variance to the standard deviation. Once we get there, we'll talk about why we do that. It just has some basic, makes things more convenient down the road. So hopefully today isn't too tough. Hopefully it's a review from something you at least have seen or thought about. Right? So if we want to calculate the mean, well, before we look at the actual formula, right? If you had to describe, let's say I had 5 numbers, how would I find the mean of those 5 numbers? Yeah, you just add them, like you inherently know how to find an average, but you probably forgot really what you're doing, right? So we really think about what you're doing. You're adding up every single value, and you're dividing by the number of values you have, right? Well, if we had a data set, right, and I wanted to find the mean, let's say I had this data set, I'll show it to you, I think, in a second, of just a bunch of different students in the letter grade they get in a course, right? Or not the letter grade, sorry, their actual numerical grade, right? I'd add up every single grade and divide by the number of students that I have in that data set. So what am I doing? I'm going to go through this variable x. I'm going to take the first observation value, add to that the second observation's value for x, add to that the third all the way until I get to the very last observation in the data set, which we'll use, kind of notate as capital N. So capital N represents the total number of observations in a population data set. So going from the first to the nth means go from the first observation to the last observation and add up all these values for this x variable. So when I'm thinking about what grade is someone getting in the class, I'm just going through, look at the first person, they got an 83, plus the next person got a 74, plus all the way down to the very last person in that data set. Once I do that, I need to divide by, you said divide by 5, divide by the total number of observations I have, right? What's the total number of observations I have in a population data set? I just said we're going to use capital N to notate that. So add the numbers up, divide by the total number of numbers in that data set. Now, I wrote it a little bit differently up here because one thing that we'll start seeing things written as is instead of writing this out every single time, x1 plus x2, dot, 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 all the way up to xn. If we use that summation sign, so that big sigma, what that's saying is go from the first observation to the very last observation and add up everything on the right side of that sum sign. Well, here, the only thing on the right side of it is the x variable. So basically start with the value in the first for the first observation for the x variable, add to that the second, add to that the third, all the way to the very last observation, capital N. And if I want to write out what that summation means, that's in that numerator there. I think what's in the second numerator, I think that's how we kind of think about it, but the notation looks a little different there. Any questions on anything here? So anytime we I first introduce notation or the mathematical way of looking at it, feel free to ask questions about the equations. I want to make sure we have as good of an understanding as we can. Like I said, I explain this in the way that we do it, but we also have to get used to start looking at how it's going to be written out mathematically. Okay? So usually saying words what we're going to do. For the sample mean, everything's the exact same. Notice now I'm looking at x bar, the sample mean. The only thing that's going to change is instead of capital N, right? My data set is of a size lowercase n. Capital N represents the number of observations in the population. Lowercase n represents the number of observations in our sample. Okay? So it's really the exact same thing, the exact same process. We just stop at a smaller number of observations, right? Because our samples will be subsets of the population. And then, an example, I use the grade example. You can also think about, and we'll work with this data set a lot this semester. I have a data set with every birth in Indiana, or you could actually pull them for the entire US. And how would I find the average weight of a child being born? Well, I could actually add up the weight of every single every single birth, and then just divide by the total number of births in the US, right? So add up every single birth weight, then divide by the total number. So it's another example of thinking about how we're going to be calculating this. All right. And I think I did this because I had the data, but it's not really that interesting. So let's think of a really easy example, right? So this is going to be, we're leading up to like a sample eye clicker, so we'll kind of use them so we can, right, make sure that everything's working correctly. But I would typically go through an example like this. So I've got some game, you might think of this as basketball, but it could be like paddle, right? Just any game where you're keeping score. Right? So I've got 7 different games, and I've got the points scored in each game. What's the population mean for points scored? So what am I going to do? I'm just going to add the numbers up and divide by the total number of observations I have in this data set. So obviously I've got 7 games, 7 observations, 20 plus 35 plus 15, all the way down here to 16. Whatever that value is, divided by 7. Right? So we write that down, right? That's what we're going to do manually by hand. I'm using a calculator. I guess you can do it in your head if you're comfortable with that. I probably couldn't come up with the second decimal what that is in my head, but I met plenty of students that are much smarter than me when it comes to visualizing that. So, all right. Any questions on this? This should be not too bad. So then I would say, okay, what if I had something like this, where I want the population mean commute time of employees at a company called ECON? It's the exact same idea. I've still got 7 observations. It's just now instead of points scored, I've got a commute time. So I add up all the commute times, and I divide by the total number of observations I have here, which is 7, right? So I typically would kind of show you something like this, right? And I'll give you a little bit of time to kind of work on it. So let's just see if everybody knows how to calculate a mean. Right? So I'll give you like a minute or so. Use this data set, calculate the mean, use your eye clicker to respond with what it is. Like I said, this will be a way we can kind of make sure everything's working correctly on not just your end, but mine as well. Yeah, I always keep it on AA. If other classes get in, like it's easy enough to screen out. I don't know why people make a big deal about it. Not you, I mean like other professors.
What does it mean when I said it's no base?
Yeah, no base.
Let's see. Let's try this again. I'm going to, I might not have set it correctly. Looks like it's set to AA. Let's try it again. You're still not seeing it? Some people have it showing up, right? Or am I picking up responses from some other class? Okay, so I'm probably getting reef results. So why would this not show up for you guys? Let me try restarting it and see if something pops up. Seeing it now? No base. Why would that not be showing up? So I've got where was the one where I could choose AA? Let's see if that. Showing up now? Probably not. All right. Well, looks like this is why I did this, right? So now I've got a thing to troubleshoot before Wednesday. So everyone
just saw no base. No one got to pull up. Those of you who are on the Reef app, you guys, it was okay? Okay. All right. So the Reef is working, but the frequency, let's try one more thing before I give up on this. Let's try to use a different frequency. I've never had to, but let's try BB. Not yet, because I gotta save it here. All right. Is that still not working? So you should just remember, right? What you hold the star button.
I have it right there, but I just don't know how to keep it. Like,
so you just hit.
What did you set it to?
BB. How did you set it on there?
I just put this down, and then that came up.
Oh, gotcha. So then you go BB.
I don't know how to like keep it there.
You want to let me do BB.
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 Yeah. I thought once you select ultimate, it's supposed to just automatically sync up.
Yeah, I never discussed before.
Maybe it's no one getting BB to show up. I think that's why it's not letting you do that. So I'll have it. Hopefully, I'll have an answer for in this class as to why we can't get this to work. All right. So scratch that for today, I guess. We'll hopefully I should be having that work, have that working Wednesday. I've got some other iClickers so I can make sure that I'm getting the frequency to show up on those. But yeah, typically I'll just use that AA frequency. Hopefully that's the one I can get working in here. That way, just kind of leave it on there and we don't have to worry about it. So any of those you actually worked through this, though, what answer did you get? Yeah, right, we get 45. So all we do is go through, we add all those commute times, right, that's our numerator, divide by the number of observations we have, which is 7. That easy, you should get 45. Okay? So like I said, these iClickers aren't meant to be hard. We typically go through examples right before it. Like this would have been hopefully easy points if we were kind of moving forward. What do I want to find the median and the mode? Okay. So the mode is just going to be the response or the value that occurs most often. So if I'm thinking about a frequency distribution, if I had this already, how could I identify the mode from a frequency distribution like this? It would just be the response with the highest bar, right? Remember, these bars represent frequencies. So wherever the highest bar is, well, that was the response that had the highest frequency. Right? So mode's not too tough, right? I mean, if we're doing it manually, we have to count them up by hand. That's kind of a pain, but we'll see in Excel, it's a little bit easier. I don't know if I'll do that today. I might save that until Wednesday. So we'll do like the variance and we'll also do like the mean at the same time. So the one that's a little bit harder would be the median. Okay. So the median is the exact middle point, the exact middle observation, right? So let's say I had 101 observations. Actually, let's make it easy. Let's say I have, I'll give you the easiest one first. Let's say we had 3 observations. So it's like 4, 8, 20. Right? To find the median, it's the observation that's exactly in the middle. So once I arrange them from smallest to largest, I can find the median by, okay, cross off the highest, cross off the lowest, cross off the net. Well, here I've got no other observations. This is the middle observation. What if I had 5, right? 5 observations, cross off the highest, cross off the lowest, cross off the next highest, cross off the next lowest. I'd still be left with that kind of 8 right in the middle because it's in the position that's smack dab in the middle of this data set once I arrange the values from lowest to highest. Now that's easy if I have an odd number data set, but what if I had an even number data set? So something like that. Right? Using small data sets here just to make it easy. So cross out the lowest, cross out the highest. Well, if I cross out the next lowest and the next highest, I'm not going to be left with any observations. So if I have an even number data set, I'm always going to have two observations in the middle, right? So what do I do then? I just kind of find the average of those two, right? So if I have an even number data set, I have a little bit more work to do, right? I have to find the average of the last two observations in the middle. Okay. Any questions on that? So how do you find the median? I had these little data sets kind of already built in. You arrange every observation from the lowest to the highest. Once I show you in Excel how we do some of these things, I'll also show you a trick for doing that in Excel. Once you have them arranged, right, you just start crossing off the highest, lowest, next highest, next lowest, until you're left with an observation in the middle. If it's even, you'll have two observations in the middle, and you'll just have to take the average of the last two, right? So kind of like one added step there, but it's not a difficult step, right? It's two numbers. Should be pretty easy to find the average of two numbers. So let's say I had a data set like this where it's not arranged, right? I've got these points scored. Once again, who knows what this game is? But what if I wanted to find the mode, right? Well, right away, I have an odd number data set. So I'm going to be left with one value smack dab in the middle, right? You kind of think about it, if I have 7 observations, well, the position that's in the middle, I think, would be 4, right? Because there would be 3 observations below it and 3 observations above it. The problem is it's only the observation that's in the 4th position after I arrange the data from smallest to largest. It's not like that yet. But what I could do, especially if it's a data set this small, look for the highest value, 35, cross that out. Lowest value, 15, cross that out. Next highest value, it's actually 235, so I'll cross off the next 35. Next lowest value, 16. Next highest value, 28. Next lowest value, 20. I'm left with that 18 that's smack dab in the middle. Now, it's a little bit easier. What did I say? Oh, what did I do wrong? I didn't read my own slides, right? I just showed you how to find the median. What did I actually ask you for? This is probably this is me showing you. Make sure you're reading questions carefully, like on the exam and things like that, right? So yes, the median is that 20, right? Right. We're left with did I cross something out wrong? We're at 28. Oh yeah, 2018. Yeah, we're left with 20, right? And this is why if you're doing it without arranging it, so you can make mistakes. I mean, a small data set like 7, it's a little bit easier for me to see what the next. I got 53 observations. I'm going to want to probably like arrange them, right? Not just do this in here. I think we do this on the next example, right? I want to arrange the data something like this. That makes it a lot easier to make sure that I'm crossing off kind of the next highest, next lowest. Now you can do it like I have animated here, where cross off the highest and lowest, next highest and lowest, next highest and lowest. I'll be left with the middle in between. But honestly, arranging it probably makes it so making it a little bit less likely to make a mistake, because you can hopefully we can all order numbers right from lowest to highest. So I had the mode up here. That was the original question. Why is the mode 35? I mean, it's the only number that happens more than once, right? Remember, the mode is the response that happens the most times, or is the most frequent. Well, here, the only thing that happens more than one time is 35, so that's going to be our mode. Okay. Now we can find the median. We've got another data set. How do I find the median for this? Well, first of all, what's the mode for this data set? I'm not sure if I asked that question in the slide, but looks like there's only one thing that happens twice again, 35. All the other observations only happen once, so the most frequent is that response of 35. If I want to find the median, I turn this into an IQ question. I might give you these responses. Well, what do I need to do? I kind of already showed you, but probably make it easiest if I arrange them from smallest to largest. Then it's just cross up the lowest, cross up the highest, next lowest, next highest, next lowest, next highest. And I'm left with that 40 in between, right in the middle. Okay. So if we're not using Excel, that's how we're going to have to find the median. I'm going to show you how in Excel makes it a hell of a lot easier. I don't want to have to do this process for 1,000 observations, right? This is going to be a pain. Okay. So why might we have these different measures? So let's see where we're at on time, and then we'll probably end this today. So why might we want to use the median instead of the mean? So I think I can give you a pretty good example. So let's say 2, 4, 6, 8. that's my data set, right? What's like the majority of the data is kind of all in one place, like between 0 and 10. But if I calculate the mean here, right, and I add all these up, I get what, 100 plus 20, so 120 divided by 5, right? That's going to be what we've got, 24. Well, to say that the value of 24 is the middle of this data set is a little misleading in the sense that, I mean, the majority of the data is below 10. How is like the middle, like when I say the majority, 4 of the 5, 80% of the observation, right? However, if I calculate the median here, cross off the highest, cross the lowest, cross off the next highest, next lowest, the median is 6, which seems a little bit more reasonable for this data set. Right? So what the median protects against, right, is extremely large values. Notice if instead this was my data set, so it's the exact same thing, it's just instead of 100 here, the observation would have been 10. Well, if I calculate the mean here, it's going to be what? 30, 10, yeah, 30 divided by 5, so 6. Excuse me. And the median, cross at the highest, lowest, next highest, next lowest. Right? The median of these two data sets is exactly the same. And it's because for both of these, the majority of the observations in both of these data sets are between 0 and 10. Right? It's just that the mean is greatly influenced by extremely large values or extremely large outliers. It would work the opposite way too. Like let's say instead of like 100, we had like negative 100 on the other end, right? It would be influenced to be much lower, right? But the median, unimpacted when we get an extremely large value, right? Because it still just counts as one place. Right? So the reason why we might want to use the median sometimes is because it's not as influenced by these extremely large values. And when we think about the naming of those distributions, it's actually directly related to the relationship of the mean and the median. Okay? So if the mean is equal to the median, we would say we have kind of a symmetric distribution or a normal distribution, right? There's no extremely large outliers on either side. And so the mean isn't really impacted negatively because there are no extreme outliers. The mean and the median end up being the exact same thing. We have a right skewed distribution. Yeah, there we go, long right tail. If we have a long right tail, what that's saying is there's some, like not a lot of observations, but there are some observations that are extremely high values, just like we had up here. Those extremely high values, we think about income, Jeff Bezos is pulling the average up a lot higher, right? A lot more to the right. So the mean gets pulled to the right, for these extremely large values, but the median is largely unimpacted, right? So the mean ends up to the right of the median. And that's really why they call it a right skewed distribution. There's a skew to that mean. The mean is being influenced by these extremely large values. So when the mean is to the right of your median, you get a right skewed distribution. Might be good to write this down. You got to, because I don't think it's anywhere in the slide. So if you have a mean above the median, you have a right skewed distribution. And you can imagine the exact opposite is true when we have a left skewed distribution. If we have extremely low values, it's going to pull the mean down to the left or pull it down to a lower value, but it's not going to impact the median as much. So if the mean is to the left of or less than the median, we say that's a left skewed distribution. Okay? So kind of drawing in those distributions we talked about with the idea of what the mean and the median represent to us and how one of them is not as influenced by extremely large values. That the one that's not influenced was the median. That's how we get the naming of those distributions. Okay? All right, 1 minute to spare. We're going to end there. I'm going to work out the bugs of the eye clickers, so expect to be using those on Wednesday. I'll also put up the first Excel and the first Connect homework. So those won't be due for another 2 weeks. The Excel, we've covered the majority of it. There's just a little bit more that we'll go through this week, but you can get a really good start on both of those. I probably won't get it posted until I'm done teaching today, so maybe around like 3:30, 4. Other than that, I'll see you guys on Wednesday.
Yeah.
I just have a question.
Yep.
I'm trying to understand the language used a little bit more. So if I'm looking at